This is the homework from page 245, 17 to 29 odd. And in this section, I just want to remind you that we are working on limits as x approaches either positive or negative infinity. And I want to remind you that literally that is about the end behavior of a function. So we're either looking for right or left end behavior. And I'm going to take a look at these particular items. Oops, edit undo. I didn't mean to do that. Edit undo. I meant to clear the annotations, so let's do that. All right, so in problem number 17, first of all, we're going to consider the function that we're looking at. In number 17, we have a rational function, and we have a polynomial in the numerator as well as the denominator. And when we have a rational function and we're looking at end behavior, that's all about horizontal asymptotes. So there are three situations when we have a rational function. Now remember, this only applies to a rational function and the horizontal asymptotes. So one scenario is our function could be top heavy. And if we have a top heavy function, that means the degree in the numerator is larger than the degree in the denominator. If we have a top heavy function, there is no horizontal asymptote, but instead there is a slant asymptote, just FYI. But the big deal is that there is no horizontal asymptote, meaning that the graph is either going off to positive infinity or the graph is going to go off to negative infinity. In either case, the limit does not exist because of unbounded behavior. So that's the scenario if you have a rational function. Remember, this is only true of rational functions, and a top-heavy situation. The second scenario is if you have a bottom-heavy function. If you have a bottom-heavy function, that means the degree in the denominator is larger than the degree in the numerator. So if that's the case, then the horizontal asymptote is y equals 0, and at the ends, right and left end behavior, the graph will approach the horizontal asymptote. So in this particular case, the limit will always be 0 because that's the horizontal asymptote. The third scenario is if you have a rational function. Again, make sure you understand this applies for rational function, and you have what I call or not just me, a same heavy situation. That means that the degree in the numerator is the same as the degree in the denominator. So the horizontal asymptote will be y equal to the quotient or ratio of the leading coefficients. That doesn't necessarily mean the first term. It means the coefficient of the highest powered degree term. All right, so I'll leave that written there, and I'm going to go over to the side because I think, in all these cases, we are looking at rational functions. So in number 17, we can see that the degree in the numerator is 2, and the degree in the denominator is 3. Because in the numerator we have x squared, and the denominator we have x cubed. So this one is a bottom-heavy. I'm just going to write down my thinking. It's a bottom-heavy rational function. Therefore, the horizontal asymptote, all of this is my thinking, is y equal to 0. Therefore, the limit as x approaches positive infinity, the right end behavior of x squared plus 2 over x cubed minus 1 will approach the horizontal asymptote of 0. So the y value that the function approaches on the right end is 0. That's letter A. In letter B of 17, we have a situation that is the same heavy because the degree in the numerator is the same as the degree in the denominator. So the horizontal asymptote is the quotient of the leading coefficients. So the coefficient in the numerator of x squared is 1, and the coefficient in the denominator is x squared. So ultimately, the first line is just the thinking. So the limit as x approaches positive infinity, the right end behavior of x squared plus 2 over x squared minus 1 is equal to 1. In letter C, we have a top-heavy rational function. We are looking at the right end behavior because x is going to positive infinity, And so in this case, there is no horizontal asymptote and there is a slant asymptote, which means the graph either goes off to positive or negative infinity. Therefore, the limit does not exist because of unbounded behavior. So that's number 17. All right, I'm going to clear those annotations, and I'm going to go to number 19 here in a moment after the annotations clear. Oops, edit, undo. What am I hitting every time that I'm doing that? So let's go to the annotations, and I'm hitting objects. That's what's happening. All right, in number 19a, we have a degree of 3/2 in the numerator, a degree of 2 in the denominator. So this is a bottom-heavy function. We are approaching infinity. Whenever we have a bottom-heavy function, the horizontal asymptote is 0, so the y value that this graph approaches is 0. In letter B, we have a degree of 3/2, and in the denominator we have a degree of 3/2, so we have a same heavy function. We are approaching, this is right in behavior because we're going towards positive infinity, so it's going to be the quotient of the leading coefficients, which is -2/3. So that means that the y value that this graph approaches is -2/3. In letter C, we have a degree of 3/2 in the numerator and a degree of 1 in the denominator. So we have a top-heavy function. Therefore, there's no horizontal asymptote. There's a slant asymptote. So the limit does not exist because of unbounded behavior. One thing you can do is to get a better understanding of this, and I think would be very helpful, would be to put some of these graphs onto your calculator so you can actually see that as you trace the graph and you go towards either positive or negative infinity, you are actually approaching these particular y values. All right, I'm going to pull the screen down or pull the slide down, and I'm going to go to number 21. So in number 21, I notice that I am looking at right in behavior because I'm approaching positive infinity. I notice that the degree in the numerator is 1, the degree in the denominator is 1, so I have a same heavy function, so I'm going to grab the quotient or the ratio of the leading coefficients. In number 23, I am again dealing with right in behavior. I have a degree of 1 and a degree of 2. Bottom heavy function, so the horizontal asymptote or the y value that I'm approaching is a y value of 0. In number 25, we are looking at left in behavior because we're traveling towards negative infinity. I have a degree in the numerator of 2, degree in the denominator of 1. I have a top heavy function, therefore there's no horizontal asymptote, there's a slant asymptote. So the limit does not exist, does not exist because of unbounded behavior. Number 27 gets a little bit tricky. So in number 27, the degree in the numerator is 1. All right, now I'm going to come over to the side, and you're going to have to deal with this. Let me circle it first. You're going to have to deal with this first term. I'm not worried about the x because I'm worried about the degree. So think of it like this. The square root of x squared gives you x to the first power. So even though it's x squared, the degree of that term is x to the first power. So technically we have a same heavy situation. Even though it looks like a power of 2, it's the same heavy situation. Now, when we have a same heavy situation, we're going to take the quotient of the leading coefficients. The coefficient in the numerator is 1, and watch carefully, the coefficient in the denominator is the square root of 1 because there is a 1 in front of the x squared right there, except I need to change colors, not right and white. So that coefficient of x squared is a 1. Now, we're still not done. So 1 over 1 gives you 1 so far, but that's not a done deal because that square root is messing with us a little bit. So now we're going to think about negative infinity. Remember, let me erase some of this stuff and get it out of the way. Remember that in this particular case we are approaching negative infinity. So if I were to let the numerator go to negative infinity, I would get a negative. So in this case we have a, I don't have time to pull my, I wish I had gotten my calculator up, but I didn't, and maybe I will in another video. But if I let the numerator go to negative infinity, and I think of substituting, even though we can't, negative infinity in place of x, I get a negative in the numerator. But the denominator, if I put a negative, very negative number in the denominator and square it, I get a positive, and the square root gives me a positive. So a negative divided by a positive is a negative. Now what's happening here graphically is this. Instead of having one horizontal asymptote for the graph in number 27, I really have two horizontal asymptotes. One is at y equal to 1, and the other one is at y equal to negative 1. And the graph does something like this. It approaches negative 1 as we go towards negative infinity and positive 1 as we go towards positive infinity. This would definitely be one to take a look at on your calculator to get some idea that there's not just one horizontal asymptote. All right, let's finish this up. Let's go to number 29. I see a radical again. So in the numerator, I have a power of 1, just like I did in the last problem. In the denominator for number 29, I have to think of the square root of x squared is equal to x to the first power, so the degree is 1, so we're in another same heavy situation. So I'm going to grab the quotient of the leading coefficients. So in the numerator the coefficient is 2, in the denominator the coefficient is the square root of 1, which is 2, but I have to do that same thing again with the negative infinity. If I let the numerator go very, very negative, I get a negative. In the denominator, whoops, I'm on the wrong problem. If I let this, but still the same thing, if I multiply 2 times a very infinitely negative number and add 1, I get a negative. And in the denominator, when I square a negative number, I get a positive. And then when I do minus a negative, I get a positive. So the denominator is going to be positive. So whenever you have these square roots, you can't just write down the number and move on. You can't just get 2. You have to pay attention as to whether you're going to get positive or negative infinity. This is going to give me a negative. So my answer for the limit is negative 2 as x goes towards negative infinity. 35 can be a bit tricky, but it really is not very tricky. So in number 35, I am looking for the limit as x goes to positive infinity. So I want to get infinitely large. 2, now watch what happens here, minus, watch what happens here. I have e down here to the negative x power. I'm going to make that into a positive exponent by rewriting that as e to the positive x. Because I have a negative power, remember I can take that to the denominator and make the power positive. So from e to the negative x in the numerator, e to the positive x in the denominator. All right, so now I'm moving towards a very or infinitely large number. So I have 2 minus 5 divided by e to a very positive number. Now let's think about that. If e goes to a very, if we raise e to an infinite power or infinitely large number, I have 5 divided by an infinitely large number. So if I take the number 5 and divide it into infinite parts, that fraction approaches a value of 0. Think about that again. 5 pieces of bubble gum shared with everybody in the world means everybody gets virtually 0 amount of bubble gum. So as x goes to positive infinity, this fraction approaches 0, and 2 minus 0 is 2. And then finally, number 37, we have the limit as x approaches negative infinity of 3 over 1 plus 2e to the x. So this time, negative infinity is a very negative number. So I'm going to substitute a very negative number in place of x, so 1 plus 2e to a very negative number. Think about the power work that we just did in the last problem. I don't want a negative power, so that becomes 3 over 1 plus, watch carefully, 2 divided by e to a very positive number. Okay? Because I had a very negative power back here when e was in the numerator, so now I take it to the denominator of the 2, and that becomes e to a very positive number. So we're back to that situation of 2 pieces of bubble gum divided by everybody in the world means virtually everyone's getting nothing. So I have 3 over 1 plus approaching 0, which is 3. So the y value of this function is approaching a y value of 3. And I encourage you and challenge you to take a look at those graphs on your calculator to get a better visual of what's really happening here.